2 rockets, 2 static fires, 1 month. SpaceX just confirmed it. July is the Flight 13 launch target. The confirmation just came from the top. But between today and that launch, SpaceX still needs to fix a broken vacuum Raptor, patch a heat shield coolant leak, and survive a wet dress rehearsal. All in weeks, not months. That's where the double static fire comes in. Ship 40 has all 6 engines ready. Booster 20 finished cryo testing. June is the only window that makes July possible. Can they pull it off? Stay with me. So before we go any further, let's be clear about something. SpaceX doesn't miss deadlines by accident. They miss them because rockets are hard, and right now, they're staring at one of the tightest windows they've had in the entire Starship program. Gwynne Shotwell, the president of SpaceX, publicly confirmed that Flight 13 is targeting July. Not sometime this summer, not Q3, July. That is a specific, public commitment from the number 2 person at the most powerful rocket company on the planet. And here's what makes that statement remarkable. She said it knowing exactly what still needs to happen before that rocket leaves the ground. So, what does still need to happen? Let's break it down. Because the list is longer than most people realize. SpaceX needs to complete static fire testing for Ship 40, then static fire testing for Booster 20, then review all the data from both tests, which historically takes days, sometimes weeks. Then install the payload. Then integrate the flight termination system. Then stack the full vehicle, meaning attach the ship on top of the booster at the launch site. Then conduct a wet dress rehearsal, which is essentially a full launch simulation, fueling and all, without actually launching, and then, if everything checks out, only then does the actual launch countdown begin. All of that in less than 60 days. Now here's the part that nobody is saying out loud. SpaceX has done this before, and they've failed timelines before too. The question this time isn't whether they can move fast. It's whether they can move fast and fix the specific problems that brought Flight 12 down. Because those problems, they weren't small. What Flight 12 actually broke, and why it matters more than you think. Let's talk about Flight 12 for a moment, because this is where the real story starts. Flight 12 was supposed to be a milestone. SpaceX had already proven they could catch a booster with the mechanical arms, what they call the Mechazilla system. And they were pushing deeper into the mission profile. But 2 things went wrong. 2 specific things. And they matter enormously for what happens next. Problem number 1, a vacuum-optimized Raptor engine. To understand why this is a big deal, think of the Raptor engine like a high-performance race car engine. It's tuned to work under very specific conditions. Now, the Raptor engines on the lower part of the rocket, the ones used during launch, operate in normal atmospheric pressure. But the engines designed for the upper stage, called vacuum Raptors, are built specifically to work in the near vacuum of space, where the air pressure is essentially 0. These vacuum Raptors look different from the others. They have a much larger nozzle, almost comically large compared to the rest of the engine, because in space you can expand the exhaust gases much further, which extracts more energy and produces more thrust. It's a clever engineering trick, but it also means these engines are more complex, more sensitive, and have almost no tolerance for the unexpected. During Flight 12, one of those vacuum Raptors failed. The exact nature of the failure hasn't been publicly confirmed in full detail, but the implication is clear. If your upper stage engine doesn't perform perfectly, your ship doesn't reach orbit. Period. Problem number 2, a coolant leak in the heat shield system. This one is almost more alarming because it threatens the vehicle on the way back. Here's how to think about it. When Starship re-enters Earth's atmosphere, it's moving at roughly 17,000 miles per hour. At that speed, the friction with the air generates temperatures that can reach over 3,000 degrees Fahrenheit on the outer surface. The heat shield, thousands of small ceramic tiles covering the belly of the ship, is what stands between the vehicle and total destruction. But SpaceX has also added an active cooling system behind those tiles. It works by pumping liquid through channels underneath the heat shield, absorbing heat before it can damage the structure. Think of it like a radiator in your car. except instead of keeping an engine cool, it's keeping a spacecraft from vaporizing. A coolant leak in that system means some sections of the heat shield may not be receiving adequate cooling, which means on re-entry, the vehicle could sustain damage, or worse. So you have two problems, one that affects the journey into space, one that affects the journey home. Neither is a minor glitch, but here's the thing, and this is what Shotwell's confidence is really based on. Both are targeted, identifiable, fixable problems. They're not signs of a fundamental flaw in the design, they're engineering challenges. And SpaceX is, above everything else, an engineering company. Two problems, both fixable, but the clock is already running. Booster 20, the 33-engine problem. Ship 40 is the upper stage of the Flight 13 vehicle, and it's first up for testing. Let's walk through where things stand. S40 completed its cryogenic campaign, what SpaceX calls a cryo-soak, in early May. Think of a cryo-soak like a stress test for the fuel tanks. You fill them with extremely cold liquid. Liquid nitrogen is often used as a substitute for the actual propellants, and you see how the structure responds. Do the tanks hold pressure? Do the seals leak? Does anything crack or deform? S40 passed. Both tanks handled the cold soak without incident. That's stage 1. Stage 2. All 6 Raptor engines were installed on S40 at the beginning of June. 6 engines, 3 sea-level Raptors and 3 vacuum Raptors, are now physically bolted to the vehicle and connected to the fuel systems. Stage 3. Transport to the test site. SpaceX issued a road closure notice covering the overnight period of June 14th to June 15th, strongly suggesting that S40 was about to be moved from the production facility to Massey's test site, the dedicated engine testing area near Starbase in South Texas. At Massey's, S40 will be secured into a test stand. Then the firing sequence begins. The first static fire will likely be short, roughly 10 seconds. This is what engineers call a confidence firing. You're not trying to wring maximum performance out of the engines. You're just confirming the basics. Do all 6 engines ignite correctly? Is the fuel flow stable? Are the pressures where they should be? Does anything leak, crack, or behave unexpectedly? Think of it like turning the key on a car engine for the first time after a rebuild. You're not taking it to the track yet. You're just making sure it starts. If that goes cleanly, and SpaceX will spend several days reviewing all the sensor data before declaring success, the second test follows. And the second one is where things get serious. That full duration burn could last close to 60 seconds. 6 engines, full thrust. The goal is to simulate as closely as possible the actual ascent burn. SpaceX will be watching for engine balance. Are all 6 producing the same thrust, or is one pulling harder than the others? Gimbal performance. Can the engines steer effectively by vectoring their thrust? Thermal behavior. Are temperatures staying within safe limits throughout the burn? And most critically, are the vacuum Raptors performing exactly as designed? That last point is not subtle. Flight 12's vacuum Raptor failure is the ghost in the room for this entire test campaign. If S40's vacuum Raptors pass the full duration firing with clean data, that's the moment SpaceX knows they've solved the problem. And that's the moment the July launch goes from ambitious target to credible plan. But what if there's a problem? Here's where it gets interesting. If the static fire reveals a new issue, or confirms the vacuum Raptor failure mode is more complex than expected, SpaceX will need a retest. And a retest means days or weeks of delay, and July starts to slip. This is exactly why the current schedule is so tight. There is no margin for a prolonged troubleshooting cycle. Testing for S40 needs to start soon and conclude successfully. 10 seconds. But everything depends on it. Booster 20, the 33-engine problem. While Ship 40 is heading to Massey's for its static fire campaign, Booster 20 is on a parallel track, and the challenges are different and arguably more complex. Booster 20 has already completed its own cryo campaign. It has passed the cold soak phase. But before it reaches the launch pad for its static fire test, SpaceX needs to install all 33 Raptor engines. 33 engines. To understand why this is operationally significant, consider the comparison. A Boeing 747, one of the most complex commercial aircraft ever built, has 4 engines. The Saturn V rocket that took humans to the moon had 5 engines on its first stage. Booster 20 has 33. 33 engines that all need to ignite within milliseconds of each other. 33 engines that each need to produce consistent thrust. 33 engines whose exhaust plumes interact with each other in complex ways that even SpaceX's best simulations don't fully capture. When SpaceX says they're proceeding carefully with B-20's engine installation, that's not corporate PR language. It's a genuine engineering reality. Each engine needs to be physically installed, connected to propellant lines, connected to the ignition system, connected to the sensor network, and then verified individually before the team even thinks about a collective firing. And then there's Flight 12's boost back burn. The boost back burn is the maneuver the booster performs after separation. Instead of continuing downrange, the booster fires some of its engines to slow down and reverse its trajectory, sending it back toward the launch site for the catch attempt. During Flight 12, that boost back burn produced what SpaceX internally described as producing enough surprises to keep propulsion engineers supplied with coffee for quite some time. That's the kind of careful understatement that hides a complicated engineering story. Something unexpected happened during that burn. The exact nature is not fully public, but the fact that SpaceX is spending significant time on the inspection and review phase for B-20 before proceeding to engine installation suggests they want to be completely certain they understand what happened, and that it won't happen again. Once all 33 engines are installed and verified, B-20 will move to the launch pad at Starbase for its own static fire. Unlike S-40's testing at Massey's, which uses a dedicated test stand, B-20 will fire its engines while sitting on the actual launch mount. This is the orbital launch mount, the same structure it will launch from. That distinction matters. A static fire on the launch pad is also a test of all the ground support systems, the propellant loading systems, the flame deflection system, the quick disconnect mechanisms, the fire suppression system. Everything has to work together. A successful B-20 static fire isn't just an engine test. It's confirmation the entire system is ready. And here's the optimistic scenario that has the space community genuinely excited. Both static fires completing in June. S-40 at Massey's, B-20 at the launch pad. 2 major milestones in the same month. If both tests clear in June, the roadmap to launch stops being theoretical. The wet dress rehearsal, the test, nobody talks about. But static fires are only part of the story. Engines fire, everything looks good, launch day is announced. Simple. Except, it's not simple. Because between a successful static fire and an actual launch, there's a step that has historically caused more schedule delays than almost anything else in the Starship program. The wet dress rehearsal. A wet dress rehearsal, or WDR, is a full end-to-end simulation of a launch without actually launching. The launch team runs through the complete countdown sequence. They fuel the entire vehicle, both the ship and the booster, with actual cryogenic propellants. They pressurize all systems. They run the terminal countdown sequence all the way down to T-minus a few seconds. And then they stop. They don't light the engines. They just verify that everything worked exactly as it should have. Then they detank, drain all the propellants, and inspect every system for leaks, anomalies, or unexpected behavior. The WDR is essentially the final exam before the launch. If it passes, you launch. If it finds a problem, you fix the problem and run the WDR again. And that word, again, is where timelines die. In previous Starship campaigns, wet dress rehearsals have uncovered issues that required additional work, additional verification, and sometimes completely unexpected fixes. Each cycle adds days, sometimes weeks. And each week lost from the schedule is a week that makes the July target less certain. This is why Shotwell's confirmation of a July target is both encouraging and sobering. She knows the WDR is coming. She knows it could produce surprises. And she's still saying July, which means SpaceX is confident they've reduced the risk profile significantly compared to previous campaigns. Is that confidence earned? Based on the data from their cryo campaigns and the focused nature of the known issues from Flight 12, yes, it appears to be. The vehicles have to be ready, but so does the ground beneath them. The launch infrastructure, the silent hero. There's one more piece of this story that often gets overlooked in discussions about engines and timelines, and it's arguably just as important as anything happening with the vehicles themselves. The launch infrastructure at Starbase emerged from Flight 12 in remarkably good condition. Think about what happens when Starship launches. The combined thrust of 33 Raptor engines, plus 6 upper stage engines during the initial seconds, generates roughly 16.7 million pounds of force. For context, that's about twice the thrust of the Saturn V. All of that energy has to go somewhere. Most of it goes into accelerating 5,000 tons of rocket skyward. But a significant portion gets redirected by the flame deflection system, a massive steel and concrete structure under the launch mount, into a water deluge system that absorbs and disperses the energy. After Flight 12, pad teams found the infrastructure in good shape. No major structural damage. No systems requiring extended repair. The upgrades and refinements made between flights are working. That's not a small thing. A damaged pad can take weeks or months to repair. A healthy pad keeps the schedule alive. And while the vehicles are being tested at Massey's, teams at the launch site are continuing to upgrade and refine the ground systems, installing improved hardware, refining loading procedures, and running through systems checks in preparation for B-20's arrival. In other words, while everyone is focused on engines and static fires, the launch site is quietly getting ready. The infrastructure is ready. Now the question shifts, not whether SpaceX can launch, but what kind of launch Flight 13 actually represents. The bigger picture, why Flight 13 is different from every flight before it. Let's step back for a moment, because there's a dimension to Flight 13 that most coverage misses entirely. Every Starship flight to this point has been, in the most honest sense, a test flight. The objectives have been mechanical. Does the vehicle hold together? Does stage separation work? Can the catch system operate reliably? These are foundational questions. You have to answer them before anything else matters. Flight 13 is different. Not because those questions are fully answered. They're not. But because SpaceX is now operating at a level of sophistication where the questions are getting harder and more specific. The vacuum Raptor issue from Flight 12 is a perfect example. It's not, does the engine work? It's, under these specific conditions, with these specific propellant flow rates, at this specific point in the mission profile, does the engine perform exactly as the model predicts? That's a completely different class of problem. And it requires a completely different approach to testing and verification. The heat shield coolant system is the same story. It's not, does the heat shield protect the vehicle? It's, does the active cooling subsystem maintain the required temperature differential across the entire belly of the ship during the specific thermal profile of this re-entry trajectory? Extraordinarily specific, extraordinarily difficult, and extraordinarily important, because getting it wrong means losing the vehicle. SpaceX is now engineering at the frontier, not just building rockets, but refining them in ways that no one has done before. And that's what makes the double static fire plan so strategically important. These aren't just confidence checks. They're data collection missions. Every sensor reading from S-40's static fire feeds into the analysis of the vacuum Raptor failure. Every temperature measurement from B-20's 33 engine firing tells engineers something they couldn't know from simulation alone. The static fires are how SpaceX answers the questions that models can't answer. There's also a competitive dimension to this that rarely gets acknowledged directly. Europe is watching. China is watching. Jeff Bezos is watching. Every static fire, every successful milestone, every flight that pushes the boundaries of what's achievable. It all sends a signal to the rest of the aerospace world about where the frontier actually is. And right now, that frontier is at Starbase, Texas. Blue Origin's New Glenn is flying. Iser Aerospace in Europe is preparing for its qualification mission. Vandenberg is expanding to support a new generation of smaller commercial rockets. The space industry is genuinely diversifying in ways that would have seemed implausible a decade ago. But Starship is in a category by itself. Nothing else being built today can match its lift capacity, its reusability ambition, or its ultimate mission profile. And every successful flight makes that gap wider, which makes Flight 13 not just a technical milestone, it's a statement, a demonstration that the most ambitious rocket program in history is not just surviving its early failures. It's learning from them, correcting them, and accelerating. The twist, what nobody is saying about the July target. Here's the part of the story that should make you sit up. SpaceX is not just trying to launch in July, they're trying to launch in July with specific improvements that directly address Flight 12's failures. That means the July launch, if it happens, won't be a repeat of what we've seen before. Here's what's actually at stake. Starship's ultimate purpose isn't test flights. It's payloads. It's deploying the next generation of Starlink satellites. It's carrying NASA's Artemis astronauts to the moon. It's eventually carrying cargo and people to Mars. None of that happens until Starship proves it can complete a full mission cycle reliably. And Flight 13, if successful, would be the first concrete step toward that proof. So when Gwynne Shotwell says July, she's not just talking about a launch date. She's talking about the moment SpaceX transitions from testing a concept to validating a system, from proving something is possible to demonstrating it's repeatable. That's the real weight behind the double static fire plan. It's not about checking boxes on a schedule. It's about earning the right to claim that Starship works. And that's a very different kind of milestone. The countdown to the countdown. So where does that leave us right now? Every system is pointed in the same direction. The only variable left is the data from these tests. The question on everyone's mind is simple. Can both vehicles complete their static fire campaigns in June? If yes, July becomes not just a target, but a genuine expectation. If one of them hits a snag, either an anomaly during a test or a data review that reveals something unexpected, the schedule compresses further. Not necessarily past July, but the margin becomes razor thin. One repeat BU-DR cycle is all it takes to close the July window. SpaceX knows that. Shotwell knows that. And yet she said July anyway. That's either confidence backed by data or pressure to maintain momentum. Possibly both. Here's what I think is actually happening. SpaceX has run the analysis on both the vacuum Raptor failure and the coolant leak, and they believe both fixes are implementable within the current timeline. The cryo campaigns for both vehicles have gone smoothly. The pad is in good condition. The ground systems are upgraded. Every leading indicator points toward a campaign that is, by Starship standards, going well. The double static fire plan, 2 major tests in 1 month, isn't just ambitious. It's the only plan that makes July possible. SpaceX isn't hoping it works. They've built their entire Flight 13 roadmap around it, which means the next few weeks of data from Massey's will tell us everything we need to know about whether July is real, or whether it's the kind of target that turns into a graduate-level lesson in patience. For the first time in the Starship program, the hardest questions are weeks away from being answered. 2 rockets, 2 static fires, 1 shot at July. If the data holds, Flight 13 won't just be another test. It'll be proof. Thanks for watching. If this analysis added value, a like and subscribe to the Space Brief means a lot. Drop your thoughts below. I read every comment. Hit the screen for more.